Alright guys, it's Ryan and I'm back at it again with Carlos and bringing you guys a physics problem. Now today we have a physics problem involving an inspired Terminator theme. After an intense fight, John Connor launches the T800 into a sea of lava with a velocity of 40 meters per second straight down. The end is near, but out of nowhere, a magic block begins to move straight up with a velocity of 131 meters per second toward the falling T800. After the block and the T800 collide, they stick together. Part A of the question would indicate to find the velocity of the T800 block system after the collision. Both the T800 and the magic block have a mass of 60 kilograms. Part B indicates how much kinetic energy was lost after the collision, and we can assume here that there are no non-conservative forces acting on the system. For this problem, for part A, the first part of the problem, we're going to have a perfectly inelastic collision. And we know this because the T800 and the magic block stick together after the collision. Because the collision is perfectly inelastic, that also means the block and the T800 have the same final velocity. And because we know that there are no non-conservative forces acting on the system, that means momentum is conserved before and after collision.
Alright, so for part A, as Ryan mentioned, there is a perfectly inelastic collision. And so because there are no non-conservative forces acting on the system, that must mean that momentum is conserved before and after the collision. So we can write that momentum initial will equal momentum final. So for the first part of the collision, or before the collision happens, we can call that momentum initial. You know that object 1, or the T800, has a mass of 60 kilograms, and it's going down, straight down, with a velocity of 40 meters per second. And we're going to consider down direction negative. And so now, there's also a magic block, or object 2, which also has a mass of 60 kilograms. And it's going straight up with the velocity of 131 meters per second. And so after the collision, we know that the two blocks stick together and that they should be moving both together, same final velocity, in the positive upwards direction. And the reason we know that is because, as you can see here, object 2 has a much larger momentum and magnitude compared to object 1. And so because originally the second object, or the magic block, has a large momentum and is moving in the positive up direction, after the collision we're going to assume that the mass, or the momentum of the first object, is going to change direction. So both of them are going to go same velocity in the same direction, into the upward direction. And so because we have that momentum initial equals momentum final, we can write out our momentums for before and after the collision. So before the collision, we know that block 1 and block 2 have momentums, or T800 and the magic block have momentums. So mass 1 times its initial velocity, or velocity 1. Same thing for the magic block. And so afterwards they stick together, so they're going to share the same final velocity, or VF. And if I were to distribute the VF, that would show that both objects would have the same final velocity after the collision. And so if we want to find the final velocity to solve for part A, we divide both sides by mass 1 plus mass 2 to get velocity final by itself. So now we have this handy dandy equation. So now we're going to substitute our values. going to find for part A, the final velocity is 45.5 meters per second.
The concept we'll be talking about in part B of the problem will be energy, and in specifics, the kinetic energy, since we need to find out the amount of kinetic energy lost throughout the problem, and we're going to need the kinetic energy formula to solve that.
Alright, for part B, as Ryan mentioned, we're going to need to have to know what the kinetic energy formula is. So it's K equals 1/2 mass times velocity squared. And so in order to find how much kinetic energy was lost after the collision, we need to compare the kinetic energy before and after the collision. So before the collision, or K initial, we have the kinetic energy of the T800 plus the kinetic energy of the magic block. And then after the collision, they stick together, so so now they're pretty much just considered as one object put together. So now we have to find that kinetic energy. So the masses combined times final velocity squared. And so in order to figure out how much kinetic energy was lost, we're going to subtract the final kinetic energy from the initial kinetic energy. So in order to do this, it's probably just much easier just to substitute in, find the kinetic energy initial, and find the kinetic energy final, and subtract. So let's substitute for kinetic energy initial. And if we plug into our calculator, we're going to find that the initial kinetic energy was 562,830 joules. So now let's substitute for the final kinetic energy. So it's their masses combined or added to each other. And the final velocity squared. And if we were to plug that into the calculator, we would find that the final kinetic energy was 124,215 joules. So now let's subtract the final kinetic energy from the initial kinetic energy, as we had said here. So if we subtract the two quantities, we're going to find that the amount of kinetic energy lost was 438,615 joules. So that is our answer for part B.
But thanks to T800's highly advanced technology, it detaches itself from the magic block instantaneously after the collision, moving at a velocity with the same magnitude of the T800 block system after the collision in part A, but now at an angle of 56 degrees. With respect to the horizontal, exactly 35.6 meters away horizontally, and at an unknown height of the T800 starting point after the collision, there's a portal that will allow the T800 to go back in time and save humanity from Skynet. However, the T800 can only make it through the portal if his speed the instant before he enters is at least 20 meters per second. And if he enters the portal at an angle between 37 degrees and 42 degrees, how much meters above the T800 starting point is the portal? Consider the T800 starting point as y equals 0 meters. And the final part of the question asks, will the T800 make it through the portal? For the final parts of this problem, parts C and D, we're going to be using kinematics. And we're going to be using the regular kinematic equations, but this time consider the motion of the T800 in 2 dimensions along the horizontal and vertical axes. That means that you have to use the vertical and horizontal components of the T800's velocity to solve this part of the problem. The only variable that relates to the 2 dimensions of motion together is time, so you will want to keep that in mind when trying to solve for this problem.
Alright, so before we get into solving part C and D, let's try to draw out this situation. But before we draw out the whole situation, let's draw out the T800's velocity. So T800 now is its own little object, its own particle, and so it's moving at velocity. Draw that a little better. So now it's moving at a velocity, with a velocity of 45.5 meters per second, and it's at an angle relative with respect to the horizontal of 56 degrees. And so now we understand that this is the motion of the T800, but in order to solve these parts, we need to find the components. We have to use the components, the vertical and horizontal components. So what I'm going to do here under this, or next to it actually, I'm going to draw another diagram that shows the components. So first, we'll draw what V is. So V is going to be red. It's going to be 45.5 meters per second. Now I'm going to use green to represent the horizontal component. One second, let me just draw the angle too. So here, because this component is adjacent to the angle, we're going to write that Vx, or the horizontal component, is equal to velocity, the velocity V, times the cosine of the angle, meters per second. So that would be the horizontal component. So now I'm going to use purple to represent the horizontal component. So V sub y initial, which equals the velocity. Sorry, I keep doing that. The velocity times the sine of the angle, because it is the opposite. This component is opposite to the angle. Meters per second. And now normally, most people would try to simplify this, but just so that way you have exact answers at the end, I'm just going to keep these components like this, including with the trig function inside. And so now we're going to draw out the actual situation. So at the bottom here, the T800 is going at a velocity like this, 45 meters per second, an angle with respect to the horizontal. And we know that change in x here to the portal is 35.6 meters. Sorry if that's kind of written badly. But here, we don't know the height yet, but we know it is here, the portal, this dot. And we're going to call this height h. We don't know what it is yet. So, we're going to assume, or we are assuming, that T800 does hit the portal, but we just don't know whether or not he's actually going to make it through. So to figure out how high the portal is, we need to find the amount of time the T800 is in the air before it hits the portal. So, in order to do that, I'm going to move up here. We need to find what the time is. So, you can use this formula. Change in x equals velocity initial, so velocity x, plus times time, plus 1/2 at squared. And because we know in the horizontal direction there is no acceleration, we can just cross that out. So now we just have change in x equals velocity x times time. Divide both sides by the velocity. Now, find the time. So substitute. And we're going to find that the time that it takes for the T800 to hit the portal is 1.4 seconds. Alright, so now that we have the time, let's try to figure out what the change in y is. So now this part of this question, this first part here that we used to find the time, that was the x component. But now, what we're going to do is find the height. So we're going to have to use the y component of velocity. So if we want to find change in y, actually, let's say we wrote it out as h. So we're going to find h, also known as the change in y, that's going to equal velocity y initial times the time plus 1/2 a t squared. And we're going to say that acceleration here is gravity, so negative 9.8 meters per second squared. So this is different from, this acceleration is different from the x component. So all I have to do now is plug everything in. And we're going to find that the height, when plugged into our calculator, is going to be 43.2 meters. Let me just double check with my calculator to make sure that is actually correct. Alright, looks like we're good. So now we have the height. So for part C, the height of the portal is 43.2 meters. So now let's get on to part D. Alright guys, so now let's solve part D, the last part of this problem. And on the left here I have some of the values we're going to need for part D. So in order to figure out exactly what the speed is, the final velocity of T800 when he hits the portal, we're going to need to find the velocities, the final velocities of both components, in both components. And so because in the x direction there is no acceleration, we know that the final velocity x is going to equal the initial, so this is going to stay the same. So the velocity x in the final velocity from the end x direction will be the same all throughout. But now we have to figure out what the velocity f final, or the velocity y final will be. So to do that, we can use this equation. Velocity final equals velocity initial plus acceleration times time. And so also I'm going to write down here that acceleration in the y direction is negative 9.8 meters per second squared. So now all I have to do is just plug it in to figure out what our final velocity in the y direction is. So I'm just going to plug it in. So we're going to find out that the final velocity in the y direction is equal to 24 meters per second. And so now we have to figure out what the magnitude of the final velocity is. So now we have both final velocities in the both directions, or sorry, two final velocities now. We're going to figure out what the final velocity is. So let's draw this diagram here. So we don't know what the final velocity is. That's what this area equals. We don't know what this is. We also don't know what the angle is, but let's call it angle theta. And so we know that the final velocity here is going to be the x component. And now we just figures this out, that VYF is equal to 24.0 meters per second. And the reason why I drew the triangle like this in this direction is because both values in the end are positive, so that means that the T800 is still going up. And so now, it's kind of like a triangle, we have to find the hypotenuse to figure out what the final velocity of the T800 is. So all I have to do, using the Pythagorean theorem, you understand that velocity final will equal the square root of their velocities squared added to each other. So that means VYF squared plus VX squared. So we plug them in, plug all our values in. find the value. So we're going to find out the final velocity, the magnitude of it, is exactly 35.0 meters per second if you round. So now we have the magnitude. So far, so good. T800 is going to have a velocity with a magnitude greater than 20 meters per second. So he's going to make it so far. He has one half of what he needs to actually make it. So in order to figure out exactly what the angle is, again, we use our understanding of trigonometry. So here we need to figure out what this angle is. And so in order to do that, we know that tangent theta is going to equal the opposite over the adjacent. And the opposite here is the velocity final in the y direction over the velocity in the x direction. So we plug this in again. And using inverse tangent, we figure out that theta is equal to, let's use our calculator here. Oh no, his final angle when he hits the portal is going to be 43.3 degrees, and that's not within our range. It has to be between 37 degrees and 42 degrees. So by 1.3 degrees, the T800 is unable to get through the portal. So unfortunately, he can't save humanity from Skynet. And this is going to be the answer for part D. So unfortunately, the answer is no.